Let's take a look at this initial value problem. We have 1 minus x minus 2x squared times y double prime plus 3 minus 2x squared y prime plus 7y equals 0 with the given initial conditions. I'm going to do part 4 of this problem first. What is the minimum radius of convergence for this power series? So let's write this as y double prime plus 3 minus 2x squared over 1 minus x minus 2x squared y prime plus 7 over 1 minus x minus 2x squared y equals 0. Clearly, we have problems if the denominator for either one of these is equal to 0. So we have singularities at 1 minus x minus 2x squared equals 0. And this factors as 1 minus 2x, 1 plus x. And so we have problems at x is equal to a half and also at x is equal to minus 1. And so taking a look at the picture, we're trying to do a series about 0, but we have a problem at 1/2, and we also have another problem at -1. So the closest problem to 0 occurs at 1/2. So the minimum radius of convergence is going to be 1/2. So we're guaranteed that the power series will converge for absolute value of x less than a half. After a half, maybe it converges, maybe it doesn't. We can't tell that without actually solving. Okay, next part, find a recurrence relationship for the coefficients. So again, let's start over. So we have 1 minus x minus 2x squared y double prime plus 3 minus 2x squared y prime plus 7y equals 0. And we're doing a power series about 0. So summation n equals 0 to infinity, a sub n x to the n. All right, we got a lot of work to do for this one. First, let's figure out y prime. Y prime is summation n equals 0 to infinity, n times a sub n x to the n minus 1. Now we do the standard trick of getting rid of the 0 term because n equals 0, the n equals 0 term goes away. And then I shift the index to get n plus 1, a sub n plus 1, x to the n. Okay, let's keep going. We also have an x squared times y prime term. So let's multiply this by x squared. We got summation n equals 0 to infinity, n a sub n x to the n plus 1. Okay, now let's shift again so that the series starts on x to the n. So I get summation n equals 1 to infinity of n minus 1, a sub n minus 1 x to the n, doing the shift backwards this time. So if I plug in 0, I get 0, a sub 0, x to the first. Plug in 1, I get 0, a sub 0, x to the first. So the shift works. Okay, next we have to figure out y double prime. So for y double prime, let me take this one and differentiate. So coming up to this line and differentiating, we get summation n equals 0 to infinity, n times n minus 1, a sub n, x to the n minus 2. Okay, now once again, let's do the shift so that we have summation n equals 2 to infinity, n times n minus 1, a sub n, x to the n minus 2. And then shifting backwards, we get n equals 0 to infinity, n plus 2, n plus 1, a sub n plus 2, x to the n. Okay, next we have x times y double prime. So let's multiply it by x. So I get summation n equals 0 to infinity, n times n minus 1, a sub n x to the n minus 1. Okay, now I could hypothetically drop both the 0 and 1 terms, but I'm only going to drop the 0 term because I'm going to shift by one step. So n minus 1, a sub n x to the n minus 1. And then performing the shift, I get n plus 1 times n, a sub n plus 1, x to the n. Lastly, for this part, we have x squared y double prime So I'll multiply y double prime by x squared, and I get summation n equals 0 to infinity n times n minus 1 a sub n x to the n. And wonder of wonders, we don't have to do any shifting for this one because I already have the x to the n term already there. Okay, so let's combine all these things and see what on earth happens to this. So I have y double prime. So let me start with a fresh sheet of paper. Okay, so we have y double prime minus x y double prime minus 2x squared y double prime plus 3y prime minus 2x squared y prime plus 7y. Okay, let's take these one at a time. Y double prime is this right here. Summation n equals 0 to infinity n plus 2, n plus 1, a sub n plus 2, x to the n. Then we have minus x times y double prime, so minus summation n equals 0 to infinity n plus 1 times n times a sub n plus 1 x to the n. Then we have minus 2x squared y double prime, so minus 2. So summation n equals 0 to infinity of 2n n minus 1 a sub n x to the n. Then we have plus 3y prime, so coming back up here, plus 3y prime, so plus summation n equals 0 to infinity of 3n plus 1 a sub n plus 1 x to the n. Then minus 2x squared y prime, so I've got minus 2 of those, minus 2 summation n equals 1 to infinity of n minus 1 a sub n minus 1 x to the n. And I'm going to put the 2 inside so I don't lose it. And also I'm going to make a little mark here just so I don't forget that this one starts on n equals 1. And so I have to be very careful that when I go to the next step, when I form my recurrence relation. Okay, finally plus 7y. So plus summation n equals 0 to infinity 7 a sub n x to the n. And all that is supposed to be equal to 0. Okay, so first let's deal with the n equals 0 case. If n equals 0, then that means 0 is supposed to be equal to, if n equals 0, I get 2 times 1, a sub 2. Then here, if n equals 0, I get 0. If n equals 0, I get 0. If n equals 0, I get plus 3a sub 1. If n equals 0, I have no contribution off this. And then finally off this one, I get plus 7a sub 0. So that's the n equals 0 term. For all the other terms, then I have a contribution from all 6 series. So let me just write it all out. I get n plus 2 times n plus 1, a sub n plus 2. Then minus n times n plus 1, a sub n plus 1. Minus 2n n minus 1 a sub n. Then of this one, plus 3 n plus 1 a sub n plus 1. Then minus 2 n minus 1 a sub n minus 1 plus 7 a sub n, and that has to be equal to 0. So I have a very messy recurrence relationship. The highest index is a sub n plus 2, so a sub n plus 2 will be equal to, then I move everything else over to the right-hand side and see what happens. Let's see. We get n times n plus 1, a sub n plus 1. There's another n plus 1 term here, so minus 3 n plus 1, a sub n plus 1. Then I have the a sub n terms. So this, when I move this over to the right-hand side, that becomes plus 2n, n minus 1 a sub n. Then I have a minus 7 a sub n. And then this last bit here becomes plus 2 n minus 1 a sub n minus 1. Then I have to divide by this part for n plus 2 times n plus 1. Okay, I can do a little bit better, but not much better. So here, let me get these together. So I have something times a sub n plus 1. So factoring out the n plus 1 times a sub n plus 1 on these first two terms, I get n minus 3, n plus 1, a sub n plus 1. On these terms, I have plus, it doesn't get much better than this. I get plus 2n times n minus 1 minus 7 a sub n. Then plus 2n minus 1 a sub n minus 1 all over n plus 2 times n plus 1. And that is my recurrence relationship. Now, for the purposes of being able to program this, let me shift the index so I have a sub n as opposed to a sub n plus 2. So everywhere I see an n, I'm going to replace by everywhere I see an n, I'm going to replace by n minus 2. So n minus 2 minus 3 becomes n minus 5. N minus 2 plus 1 becomes n minus 1. Again, n minus 1 down here, plus 2 times n minus 2, n minus 3 minus 7, a sub n minus 2, plus 2 times, replacing n by n minus 2, I get 2n minus 3, a sub n minus 1, all over n times n minus 1. And that's going to be my rule as long as n is greater than or equal to, for starting on terms basically 1 and higher. Okay, yuck, what a mess. Let's talk about how to program this in the computer. And one other thing before I go further. This line is true if n is greater than or equal to 1, which means the subscript is 3 or higher. So this rule is true if the subscript is 3 or higher. Okay, so let's talk about how to program this. First, let's go back to this one. So this means that a sub 2 is going to be equal to minus 7a sub 0 minus 3a sub 1 all over 2. And so attempting to put this in Excel is going to be a bit of a mess, but let's illustrate how this would work. So column A, I'm going to leave a lot of room here for column B. So row 1, row 2, row 3, row 4, row 5, row 6. Here are going to be my values of n, which I'll fill down this way. So this will be 1, 2, 3, 4, 5. Okay, now let's take a look back again at the original initial value problem. We were given that y of 0 is equal to 2. That's a fancy way of saying that a sub 0 is equal to 2. We're also given that y prime of 0 is equal to 4, which is a fancy way of saying that a sub 1 is equal to 4. So these numbers are given to us in the initial value problem, 2 and 4. Okay, up here we figured out how to solve for a sub 2. So a sub 2 is going to be equal to 7 times a sub 0, so minus 7 times b1, then minus 3 a sub 1, so that's going to be this term here, minus 3 times this term, all divided by 2. That's the divided by 2 part I see here. So that's going to be how I figure out the second term in the series expansion. To get every other term in the expansion, it's going to be this thing here, so that's going to be equal to, okay, here goes nothing. N, so a 4 minus 5 times a 4 minus 1 times the previous term plus 2 times n minus 2. I could write out a 4 minus 2. I can also just simply go 2 back, so that's going to be a2. N minus 3, I can go 3 back to a1 minus 7. times the term that's 2 back, plus 2 times a n minus 3, so that's going to be the term 3 back, times a sub n minus 1, or that's just, I shouldn't have 3 here, I apologize. So that's going to be term that's 3 back, so b1. Okay, that's the numerator, divided by n times n minus 1, so that's going to be a 4 times a 3. And so that is most definitely a mess, but that is the way that Excel can be used to confine the terms of expansion. And then, of course, we would fill down the pattern to get the rest of the terms. Okay, finally, the question asks us to actually figure out all terms up to x to the 4th by hand. So there's no shortcut to this. Let's just do it. So a sub 0, just a reminder, that's equal to w0 over 0 factorial from the Taylor series expansion, so that's equal to 2. A sub 1 is equal to y prime of 0 over 1 factorial, courtesy of the Taylor series expansion, and that's equal to 4 over 1, or 4. A sub 2 is going to be found by using this formula here, so minus 7 a sub 0 minus 3a sub 1 over 2. So that's going to be minus, let's not do that, minus 7 times 2 is 14, minus 3 times 4 is 12, all over 2. So that works out to be negative 13. A sub 3 is equal to, okay, now we have to use the formula that I see here at the top of the screen. So a sub 3 is going to be equal to, plug in 3, I get negative 2, times 3 minus 1 is 2, times a sub 2, plus 2 times, plug in 3, I get 1 times 0, minus 7, a sub 1. Then plug in 3, I get 2 times 0, times a sub 0, all divided by 3 times 2. And so this works out to be negative 4 times negative 13. Then I have minus 7 times a sub 1, which is 4, all divided by 6. And if I do the arithmetic correctly, I believe that works out to be 4. So that's 52 minus 28 is 24, divided by 6 is 4. Finally, a sub 4 will be equal to, and again I use the formula that I see here. So plugging in 4, I get negative 1 times 3 times a sub 3, plus 2 times 1, minus 7 a sub 2, plus 2 times 1 times a sub 1, all over 4 times 3. Okay, so that's using the formula. Now let me unfold the top sheet of paper here. Here I have negative 3 times 4 for negative 12. Here I have 4 minus 7 is negative 3. Negative 3 times negative 13 is plus 39. And then I have 2 times a sub 1, that's plus 8, all divided by 12. And I believe that works out to be, let's see, so this is going to be 27 plus 8 makes 35 over 12. And so our series expansion is going to start off like this. Y of x is going to be equal to 2 plus 4x, then minus 13x squared, plus 4x to the third, plus 35 twelfths x to the fourth, and so on. So that's how the first few terms of the power series expansion. And by taking multiple terms of the expansion, we can get accurate approximations to the value of y just by taking as many terms as necessary. And again, this series ought to converge for all values of x, absolute value of x less than 2. So this converges absolutely if absolute value of x is less than a half. We showed that earlier. And it's possible that it might converge for other values as well.